Math, math, it's all about math, 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 the wonderful world of math. Welcome to the wonderful world of math. Today we're going to do area between polar curves again. Last time we super lucked out when the intersection of our two curves was a nice number. So today we're going to do an example where it is not a nice number. Refresher. The region bounded by polar curve and the rays, where f is a positive continuous function, and the difference between our two theta values is less than or equal to 2 pi, but still positive, gives us an area based on this definite integral that was based on the area of a sector of a circle, right? That's where we got this from. And we talked about that last time, and now we talked about this last time too. If we have two positive continuous functions, one of which is further away from the pole than the other, then I can talk about the region between them. The area of the polar region between two curves is going to be just like when we did the area between two curves in rectangular coordinates. You're going to subtract the two areas, the area between F and the pole, and the area between G and the pole. That says Y of theta. That should say G of... No, it's just a funny looking... There we go. G of theta. Subtract this area from this area, and you'll get the purple region. Right, but because these have a common factor of 1/2, and because the limits of integration are exactly the same, that just turns into this when you use the properties of the definite integral. And this is nice. This is what we're going to do in this video. So for our example, we want to find the area inside this curve and outside this curve. We would like to graph each of these curves. We would like to identify the region on our graph that we would like to find. We would like to find the intersections of these two curves so we can set up our integral. In order to figure out what integral to do, I need to know the two curves. Well, those are kind of given to us, but I also need to know these two theta values. And that's what those points of intersection are going to tell me. I can solve for the points of intersection, but unless I'm really careful and really good at it, I'm not necessarily going to get all of my intersection points. Graphing polar curves can really help you know how many you should have and find some of them that may prove stubborn. So let's set up a table of values for each of these curves. These curves are both based on sine, so we're going to plug in the quadrantal angles as well as anything with a reference angle of pi over 6. Let's start with the first quadrant. Definitely 0 and pi over 6, and we're definitely going to want pi over 2, right? How much more than that do we want? Depending on how comfortable you feel with curves of the greater limacon family, including cardioids and convex limacons and dimple limacons and limacon with loop, you may want to graph more or less points. Depending on how comfortable you feel with symmetries in polar coordinates, you may want to graph more points or less. Now I feel pretty great about symmetries, so we're going to do that. Curves in the limacon family that have signs in them like this, we should expect to not be symmetric about the x-axis, theta equals 0. When you replace r with r and theta with negative theta, you get r equals 3 plus sine of negative theta, but because sine, unlike cosine, is an odd function, this becomes sine of theta with a negative in front of it, and there's no way this is going to be equal to the function you started with, right? So how does symmetry about the y-axis look? That means that if I've got a point over here, r comma theta, I want a point over here called r comma pi minus theta. So that if I were to add this and this, I would get pi, right? Adding this and then this. Now if this was supposed to be a mirror of this, then that means that this angle and this angle should be the same, right? They should be mirrors of each other. So this plus this should add up to pi. Pi altogether, and theta here This is going to have to be pi minus theta. So let's show that for this guy. R equals 5 minus 4 sine theta. Now we want to replace r with r. Okay, that's easy. And we want to replace theta with pi minus theta. That's a little trickier. Pi minus theta. Recall that the sine difference angle identity is going to be sine of the first times cosine of the second minus sine of the second times cosine of the first. This is minus, this is minus. That is how it works for sine. So now r equals 5 minus 4 times parentheses, because this one factor is going to turn into two terms that still have to get multiplied by 4. Sine of the first angle, sine of pi, times cosine of the second angle, that's cosine of theta, minus sine of the second angle, sine of theta, times cosine of the first angle, cosine of pi. What is sine of pi? Right? We know what sine of pi is. So we can simplify this. And rather than have to write a whole bunch of stuff, we'll just say all of this cosine theta times 0 is already 0. Now sine of theta times cosine of pi. Cosine of pi is negative 1. So we have this double negative, negative times negative, which is actually a triple negative, 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 all being multiplied together to give you r equals 5. 3 negatives means it's still negative 4 sine theta. Now this is equal to what we originally started with, so this is symmetric about theta equals pi halves. Now, I'm not going to do the other one. It works basically the same way. You've seen how this one works. You should be able to do the other one on your own. Check it, please. Now, back to business. Since this is symmetric about the line theta equals pi over 2, I don't really have to do all 4 quadrants. I have information about what's happening here, and I know that tells me about what's happening over here. If I also know what's happening over here, that will tell me what's happening over here. I need to do 2 quadrants max. You can do the first quadrant, good choice. We've already got stuff listed here. And you can do the 4th quadrant or the 3rd quadrant, but we've got to do one of them. Now this should be enough to get us started. When I plug in 0 for theta, this becomes 5 minus 4 times 0, 5 minus 0, r is 5. When I plug in pi halves, sine of pi halves is pi halves. Here's pi halves. I was mixing up the value of sine with the angle. Pi over 6 in sine is equal to 1/2. 5 minus 4 halves is 5 minus 2. This is 3. Now, when I plug in pi halves, sine is at its maximum. So I am subtracting the most possible. 5 minus 4 times the most is going to be the least overall. Since I'm subtracting as much as possible, 5 minus 4 is 1. This is my minimum value. Now, when you do this stuff in the 2nd quadrant, 5 pi over 6 is going to get you 3 again, and pi is going to get you 5, right? Because sine of pi and sine of 0, both 0. Into the 3rd quadrant, we're getting some new r values. Sine of 7 pi over 6 is negative 1/2. So now we've got 5 minus 4 times negative 1/2. Negative negative is positive 4 halves. 5 plus 2. This is going to be 7. And now when I plug in 3 pi over 2, this is going to be negative 1. 5 minus 4 times negative 1 becomes 5 plus 4. 9. And when you do the 4th quadrant, you'll get another 7 r value at 11 pi over 6. And this is the bare minimum. So plotting some points, we've got 5, 0, 3, pi over 6, and 1, pi halves. And we figured out from symmetry that we're going to get the mirror images of each of these things. We're going to get 3, 5 pi over 6, right? So 3, 5 pi over 6, and we're going to get 5, pi. We also said that in the 3rd quadrant, when we've got 7 pi over 6, we're supposed to be at 7. So 7 pi over 6 gets us 7. And that we've got the mirror image of this guy at 11 pi over 6, also 7. And then at 3 pi over 2, we had 9. Now, this isn't a ton of information. If you want to fill in some more gaps, a good place to do that would be, say, here, where we've got 3 lines in a row with nothing on them, and same here and here. So if you want some more, here's a good selection of some more things. Obviously, I left out a few. I didn't do 5 pi over 12 and pi over 12. I didn't do 13 pi over 12. You could do those ones too. Now, check these guys out. Plug them into this equation and see what r is. Checking your work in 3, 2, 1. Here we are together. And this gives us some more things to plot to get a better idea of the shape of the graph. Pi over 4 comma 2.17. Now we can't really do better than 2.2, so we're just going to round that a little bit. 2 and then a tiny bit more, right? Now at pi over 3 you're going to have 1.54, or about 1.5. You can't do much better than that. And you're going to get the mirror images of each of these. So you get one there, and you get one here at approximately 2.2. Now, down in the third quadrant, we've got 5 pi over 4 giving us approximately 7.83 or 7.8. So that's 5 pi over 4, 7 point, most of the way to 8. And you get its mirror image at 7 pi over 4, most of the way to 8. And at 4 pi over 3, we also did that one. It's going to be 8.46, or approximately 8.5. So you get that and its mirror image. And we had one that was just a little bit closer, approximately 8.86, right? Or almost 9. Now this is a pretty good picture of what's happening with our graph. We see that it should look like a dimpled limacon. Alright, now that's a little better. Then we still have to do the other graph. So here's a smattering of some good things to plug in. 0. 3 plus 0, check. Pi 6, I did the thing again. Pi over 6 turns sine into 1/2. 3 plus 1/2, you can call it 3.5. We're going to have to use decimals for the weird stuff anyway. Pi halves. 3 plus sine of pi halves is 3 plus 1. 5 pi over 6. This thing is symmetric about theta equals pi halves. This is going to give us the exact same thing as pi over 6. Sine is positive in both the first and second quadrants. Same values. Pi. Well, sine of pi is 0, so this is the same thing as sine of 0, because again, it's symmetric about that old y-axis. Now 7 pi over 6 is different. Sine of 7 pi over 6 is negative, because 7 pi over 6 is in the third quadrant. 3 plus negative 1/2, 3 minus 1/2, or 2.5. To the decimal aficionados. 3 pi over 2 makes sine negative 1. 3 minus 1 is 2. Now that is as much as you can possibly take away. That is the minimum value. And then 11 pi over 6 is just going to be 2.5 also. So plotting those, you get 1, 2, 3, 0. You're going to get 7 halves, or 3.5 at pi over 6. So pi over 6, 1, 2, 3.5. Notice that this is further out than the blue graph right now. Now at pi halves, you're at 1, 2, 3, 4. And then we didn't do anything else in between here and 5 pi over 6. So that's going to be 3.5, comma 5 pi over 6. And then back to 3 when you hit pi. In the third quadrant, 7 pi over 6 makes us 2.5. So 2.5, and you get its mirror image at 11 pi over 6. 2.5. Marvelous. At 3 pi over 2, we are our minimum value of exactly 2. And when we connect these dots, we get a curve. Alright, now that looks a little better. Now, there are a bunch of regions here. We've got a region here. We've got a region A, and a region B, and a region C, and a region D. Which one is the region we want? Now, A doesn't look like it's inside anything. It's outside of everything. C is in both of them. That one is also not our region. We wanted something inside one of the curves and outside the other curve. So which one is it? We said inside r equals 5 minus 4 sine theta, so it's inside here. So that means it's either C or D, and we already knew we wanted something that was outside of one of the curves. That leaves outside the green curve. So it can't be C. It's got to be D. This is the region we want. This region here is our R. So now we know who's farther away from the pole on this region. The next thing we need to know is, where do these things cross? Where am I going to be integrating from? What are my limits of integration? I need to know the two theta values. So where do these intersection points happen? Where does the blue curve take over as being the further away? The one that is the outer bound, as opposed to the green one, which at this point here starts being the inner bound. Where does that happen? We need to find those intersection points. Where is this one curve equal to this other curve? Good news, this picture tells us how many intersection points to expect. 2. So when we go out looking for the intersection of these two curves, we should expect to find 2 answers. One in the first quadrant and one in the second quadrant. Now, intersection points typically are found 2 ways, elimination or substitution, and when we have nonlinear systems of equations like this, we typically want substitution. So we're looking for a point r comma theta that's the same r comma theta on both equations. So if this r and this r are the same, hey look, I can set 2 things that are equal to r equal to each other. 5 minus 4 sine theta is equal to r, but so is 3 sine theta. Right? So now we just solve for theta. Add 4 sine theta to both sides. 5 equals 3 plus 5 sine theta, and then subtract 3 from both sides. 2 equals 5 sine theta. Dividing both sides by 5, you get sine theta equals 2/5. Now this doesn't have a nice answer. That's the whole point of doing this example. What this tells us is that arc sine, or inverse sine, of 2/5 is equal to theta. But that's only part of the story. This does give us an angle, and it is in the first quadrant. It is between 0 and pi halves specifically. Now, we know that there are 2 intersection points. So this is going to be the theta value arc sine of 2/5. What is this going to be? Well, it's going to be its mirror image over in the second quadrant. How do we find the mirror image of this guy over here in the second quadrant? Now you can go back to what we learned about reference angles, or you can take a cue from what we did earlier about finding symmetries. This is going to be theta minus pi minus theta. Pi minus theta has the unenviable name of pi minus arc sine of 2/5. Yikes. And there's not really a better way to express that. Okay, are you ready? There's a lot going on in this problem, and we haven't even set up the integral. To integrate, we want to be able to go from a theta value to a theta value, right? Except the problem with this is that this is between pi halves and pi, and this is between 0 and pi halves. You're not going to get there from here going in the correct positive counterclockwise direction. If I start between pi halves and pi, and I go around to this angle, I'm not going to end up between 0 and pi halves. I'm going to end up between, wait for it, 2 pi and 5 pi halves. So I should like an angle that is in that region, right? So another way to describe this angle, or theta equals, yuck, you just add 2 pi to the one you started with, and ta-da, it's going to fit. This now is between 2 pi and 5 pi halves, so that if you go from this angle to this angle, that will be a nice circuit. So this is what I've got to fill in. I've got to fill in alpha and beta, the lower limit of integration and the upper. Now we've just gone through it extensively. Alpha is going to be arc sine of 2/5 subtracted from pi. Yuck. And beta was going to be 2 pi plus arcsine of 2/5. Cool. And the inner and outer, we figured that stuff out, thank goodness. So that the outer function here was going to be 5 minus 4 sine theta. You gotta square that. And the inner function was going to be 3 plus sine theta. And you gotta square that. And now allow me to make this, finally, slightly better. This was symmetric about the vertical line theta equals pi halves. I don't actually have to go from here all the way to here to find my area. All I really have to do is go from here to here and multiply by 2. I'm going to find this area and use symmetry to get this area. Pretty handy, right? So we're going to multiply the whole thing by 2. Now that's 2 times 1/2. That sounds like it's going to be nice in a second. But this is still pi minus arcsine of 2/5. Nothing we can do about that. But now, stopping right down at the middle, 3 pi over 2. Okay. That's going to be so much better. Now this and this, you will have to FOIL. 5 squared minus 2 times 5 times 4 times sine theta plus 4 squared sine squared. 16 sine squared theta. And you're going to have to FOIL this one too. 3 squared plus 3 times 1 times 2 sine theta plus sine squared theta. And then you're going to distribute and combine like terms. Of course, on the next line, it's really helpful now that we can just 2 times 1/2 that out of there. Still pi minus arcsine of 2/5 to 3 pi over 2. That's the improved version, remember. 25 minus 9 is going to be 16. Negative 40 sine theta minus 6 sine theta minus 46 sine theta. Positive 16 sine squared minus sine squared, positive 15 sine squared d theta. Now, these two guys, they're going to be pretty easy to do. But this one is going to require two things. It's going to require the power reduction formula for sine, and after that, u substitution. Now the power reduction formula says sine squared of an angle is going to be 1 minus cosine of twice that angle all over 2. This was derived from one of the cosine double angle formulas, and there we go. So we've separated the easy to integrate stuff over there, and now we've got 15 times this integral from there to there of 1 minus cosine 2 theta over 2 d theta. On the next step, we'll move this factor of 2 from the denominator out into the front, where it becomes 15 halves. And we will integrate each of these things, but then we'll also have to do a u substitution here. Antiderivative of 16 with respect to theta is 16 theta. Antiderivative of sine theta with respect to theta is negative cosine. So we change the sign in front of the trig function, and we get that evaluated from one to the other. Now over here we want to do a u substitution. It's an easy u substitution, but we've got to make it because du is not just equal to d theta, it's 2 d theta, or 1/2 du is equal to d theta. We also have to change the limits of integration, so this is kind of terrible. U of 3 pi over 2 multiplied by 2, you just get 3 pi. That's not that bad. But u of this monster, you just multiply both of these terms by 2. Evaluating the first two guys at the end of the limits of integration, we get that stuff. This we have to talk about. This, thankfully, is 0. This simplifies nicely. This we'll have to distribute. And this factor of 1/2 and this 15 halves combine to get 15 fourths. Now this has two things we have to worry about. Number one, this is a difference of angles, so you got to use the cosine difference angle identity. Cosine of the first times cosine of the second, that's right, cosine of that, minus sine of the first times, it doesn't really matter what I'm going to write after this because this is sine of pi, that's going to be 0. So sine of blah 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 blah, it's 0. Thank goodness. Because wait, we're not done yet. I have to find the antiderivatives of these with respect to u. So antiderivative of 1 with respect to u is u, and then integral of cosine u du is sine u. I'm going to evaluate both of those at this. Now these guys are like terms, combine them. This stays that way. Cosine of pi is -1. Of course it helps if you don't forget to distribute this minus sign. That should have been here. So -1 is going to end up making that thing a plus now. So now we've got this after evaluating those two dudes at the limits of integration. This is basically done for now. This is done for now. This still has to be talked about. And this needs to be distributed. So boom. And now we can combine like terms. Sine of 3 pi, 0. Now let's think about this. You could use the sine difference angle identity, but mostly this is just a periodic function. And so you take sine of some angle, and sine of 2 pi plus that angle is always going to be the same thing because its period is 2 pi. So anytime you have plus 2 pi, you can just ignore it. So we distributed the 15/4, and we used the period of pi to say that this plus 2 pi doesn't mean anything. Now we will use the odd identity of sine to say that this can come out in front. And now we're going to combine like terms. 8 pi is equivalent to 32/4 pi, and 32 plus 15 is 47. 16 is equal to 32 halves, so 32 plus 15 halves. And now we're going to bust out some serious last-minute trigonometry to simplify this and this. Both of these are going to require right triangles. That is all this one needs, but this one will also require the sine double angle identity, sine of 2 times an angle. So the sine double angle identity says sine of twice an angle is sine of the original angle times cosine of the original angle times 2. So to do this, you first of all have to think of sine inverse of 2/5 as an angle. This is pretty natural, because that's kind of what it's supposed to do. It's supposed to take in a ratio of side lengths of triangles and give you out an angle. Now, assuming that angles are in the right places, this is equivalent to saying sine of that angle theta is equal to 2/5. Now sine, SOHCAHTOA, is opposite over hypotenuse, which means that you can draw a triangle here where you've got a theta, and the opposite is going to be 2 and the hypotenuse is going to be 5. Using the Pythagorean theorem, you figure out the adjacent side. Opposite squared plus adjacent squared equals hypotenuse squared. So the adjacent side is the square root of 21. Well, why is this important, you say? Well, as we just mentioned, sine inverse of 2/5 can be thought of as the angle theta. Now, using the double angle formula, that's going to say 2 times sine of theta cosine of theta. Well, now that I've got this triangle, I can figure out sine of theta and cosine of theta. Sine of theta is going to be, well, that's the 2/5, isn't it? And cosine of theta is going to be adjacent over hypotenuse. So this expression is actually this. So we've just discovered that cosine of this angle theta is going to be radical 21 over 5, and that this turns into 15/4 times 2 times sine of arcsine of 2/5, which is 2/5, times cosine of arcsine of 2/5. Now, one of the factors of this 4 cancels with this 2, and the other one cancels with this 2. One of the 5 factors of this 15 cancels with this. You're left with a 3 here and a 5 here. Whew, I was starting to think we wouldn't make it, but there it is. That is our exact answer. So when you've got not nice intersections like that, you're going to have to use a lot more of that sneaky last-minute trigonometry and right triangles. Our word of the day is the oviraptor, the egg thief. And this has been a Badger Bear production of the wonderful world of math. See you next week. Same bear time, same Badger channel.